Okay, Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome back to another session. And today we are talking about impulse. And what is impulse? So, we're going to find out in just a minute. Basically, impulse is defined as the change of momentum, but what does that actually mean in reality? So, I want you to imagine like you're playing basketball, okay? Like when you throw a basketball to someone else, you push on the ball, right? Like you push on the ball. Uh, that push is basically like a little burst of force. Now, if you throw the ball really hard and it stops suddenly when the other person catches it, that's because of the force you put on it, okay? That sudden stop is what we call impulse. Okay, so if it stops suddenly, you've gone from momentum to zero. There's a change in momentum. So the initial momentum is such, is say for example, 3 kilograms dot meters per second to suddenly zero. That is momentum. That is impulse. The change in momentum. Okay, so the impulse is like a big push or pull that changes how something moves. When you throw or catch things, or even when you kick a ball, you're giving it an impulse, okay, by changing its motion with a push. It's like this special oomph that changes how something moves, okay. It's like basically like if somebody throws a ball at you and like they throw a ball at you really hard. Now you have two options. You can catch it suddenly, like okay, catch it suddenly, and you can feel the amount of force, and that's really quite hard. Or you can try and slow it down. Okay, so you can try and basically catch it, but then not so suddenly, like slow it down a bit by moving your hands backwards. That is impulse. Okay, in short, that is impulse, an example of impulse. If you try and slow something down, let's see if I can show you a quick example. So here I have an object. I have a phone, okay, and I'm going to try and hold it. See, that represents a sudden change in momentum, also known as impulse. Now, I want to give you another example of how I can do this is if I take my hand down a bit as that falls down, then I've changed the time. I've changed the time, and therefore I've changed the impulse. But we'll come to talk about that a bit more. Okay, so for now, if that didn't make a lot of sense, don't worry. Once we start doing the questions, inshallah, it will make some sense. And also, we're going to watch a video as well that will clarify things. So we talked about momentum before, and we know that momentum is equal to, what is momentum equal to? Momentum is equal to mass times velocity. Okay, so impulse is also a vector quantity, as you would have noticed, and it's equal to the force multiplied by the time. So you can see there are two factors influencing impulse, the force and the time. Um, but it's also equal to something else. Impulse is equal to change in momentum, which means final momentum minus initial momentum. And that will come in handy soon. I don't want you to worry so much about the formulas. I find that it's a lot easier to understand them rather than memorize them as we start doing the questions. Okay? But since impulse is basically equal to change in momentum, or P final minus P initial, then the unit for impulse is going to be the same as the unit for momentum. So it's kilograms dot meters per second, which is what we see over here. Okay, there you go. It can also be newtons dot seconds. That is perfectly fine, which is why you see that over here. Okay, let's move on. So here's a question. Um, you push on a 22 kilogram shopping cart, so that's mass obviously, with a force of 6.5 newtons. So that's the force. If you push for 1.9 seconds, that's the time. What is the magnitude of the impulse you deliver to the cart? We already know that impulse is equal to force times change in time. Okay? And if you're more happy with a triangle, then we can do the triangle. Impulse equals force times change in time. Okay? So what are we being asked for? What is the magnitude of the impulse? So we need to find what the impulse is. So that's going to be force multiplied by time, simply speaking, so which is equal to 6.5 multiplied by 1.9, and that equals, let me just get my calculator, 6.5 multiplied by 1.9, 12. We working with two significant figures? Yes, we are. So 12. 12 what? Kilograms dot meters per second. Or you can go with newtons per second. Newtons second. Okay, both are perfectly fine. Let's look at question 15 and see what we can do there. Question 15 says, you kick a soccer ball, delivering an impulse of 23 kilograms dot meters per second. If the force you exert on the ball lasts for 0.25 seconds, what is the magnitude of the force? So we have the impulse and we have the time this time. We have the impulse and we have the time. We need to find the force. So obviously force is going to equal the impulse divided by the change in time. So we have 23 divided by 0.25, and that's just going to equal 23 times 4, which is equal to 92 newtons. Okay, that is question 15. Easy as that. Question 16. Use a different color, slightly darker. Apple 1 falls from a tree and drops 2 meters to the ground. Apple 2, which has the same mass as Apple 1, falls from the tree and drops 3 meters to the ground. Is the impulse delivered by the gravity to Apple 1 greater than, less than, or equal to the impulse delivered to gravity by Apple 2? Interesting question. I'm going to go with green, and you'll see why in a minute. So I'm going to draw the tree. I'm going to draw the tree. And then I'm going to draw the branches. And here we are. That's the tree. And then I'm going to draw the apples too. So we have one apple that falls from here, which is 2 meters. We have another apple that falls from here, which is 3 meters. This is not very accurate. So this is 2 meters, this is 3 meters. Now what are we being asked again? We're being asked about the impulse, so which impulse is greater? Now remember the formula for impulse. So that's force times change in time. So the gravitational force acting on the apples is presumably the same, since, does it say that they're the same? Oh yeah, it does. So it says they're the same mass. So obviously, since they're the same mass, then it's the same weight. And so the gravitational force is exactly the same. So F is going to be the same for the 3-meter apple as it is for the 2-meter apple. But does that mean the impulse is going to be the same? No. Why not? Because the 3-meter apple is going to take longer to reach the ground than the 2-meter apple. And so, because the 3-meter apple is going to take longer, the impulse is going to be greater. Okay? So, what is it asking for? Which one is drops from 2 meters? Apple 1 drops from 2 meters. So this is Apple 1. I should actually just label them. And this is Apple 2. And so what is it asking? It's saying, is apple 1 going to be less than, it's going to be less than, apple 1 is going to be less than apple 2 because the time is longer for apple 2 than apple 1. Okay? As impulse changes an object's momentum, excuse me. Yes, so change in momentum, which is referred to by this triangle, change in momentum. Just a quick note here, momentum, why is momentum P? I had a student ask me that. So turns out in Latin, the word for momentum, where P comes from, is pelere, which is, it's actually very close to Italian for pelo. Pelo means push or strike, like striking with a hammer. So pelere is just another form of that, like a forcefully strike something. So that's where the P comes from, like it's a sudden strike. So that's why momentum is like that. Excuse me, I need to enjoy my coffee. Excellent. Right. So we already mentioned that impulse, the formula for impulse is F multiplied by change in time. Well, impulse is also equal to change in momentum. So I is exactly equal to change in momentum. So we can actually replace we can replace that with change in momentum is equal to force multiplied by change in time. That's all that's saying. Okay, that's all that's saying. And of course, change in momentum means P final minus P initial. Okay, easy. Let's do more problems and it'll make more sense, inshallah. Oh, we've got a video to watch. That's always good because that makes things a bit more sensical.
We're going to be looking at some applications of the impulse change of momentum relationship. Okay. Now, according to that relationship, the impulse is equal to the change of momentum. As an example, suppose that I drop this brick to the table. Now, in the collision, the brick underwent a change of momentum. That's its final momentum minus its initial. The final momentum is what it has now when it has come to a stop, so that's 0. The initial momentum is what it had at the instant that it hit the table, and that depends upon how far I dropped it from. Now, if I were to drop the brick on this cushion, its change of momentum would be the same as it were for the table because the brick comes to a stop. That's its final momentum, which is 0. And its initial momentum is what it had at the instant it hit. And if I drop from the same height, that's the same as it was for directly on the table. What is different in these two cases is the amount of time that the collision lasts. In the case of the cushion, you can see that the cushion depresses. You can see the cushion compress, and that takes more time than if I drop it directly on the table.
Yeah.
So you can see what the purpose of a cushion is. That's the cushioning effect that you get. Is basically it's increasing the time that the collision lasts. When you walk across a carpeted floor, you have the same sort of a situation. For each step on the floor, you feel less force than if you were to walk across a concrete floor, for example, because the duration of each collision is less. Another example of that is when you jump from a height. When you hit the ground, as you hit the ground, you always bend your knees.
Of course.
That's essential if you want to protect your bones. Because by bending your knees, it makes that collision last a lot longer, and as a result of that, the force of the impact is less. If you didn't bend your knees, you do serious damage to your bones and to your joints. Now, we can apply the impulse momentum relationship to another situation where, in fact, we want to make the force as large as possible. When you pound a nail, you want greater force, not less force. When I drop the hammer on the head of the nail, the hammer undergoes a certain change of momentum while it's colliding, from whatever it had at the instant it hit to 0 when it comes to a stop. So again, that side of the equation is fixed.
Bring down the time,
so if I pound with the piece of wood on the table, my collision is going to last a lot shorter time than if I pound with my block of wood on the cushion. Obviously, you'd never try doing something like that. That makes the collision last too long, and so the force is going to be correspondingly small. You always have a hard surface underneath it. That makes the collision last for a shorter period of time.
Excellent. So the gist of that is this, basically, that since momentum is the same, by playing with either of those factors, either the force or the time, or mainly the time, we can change the force. So what that means is this, right? If we have a ball and the ball is moving and you try and catch the ball, right? If you try and catch the ball and it hits you all of a sudden in such a short time, then the force is high. The force is going to be quite high if the time is low. So if the time is low, that means it hits you and the ball goes just like that, then you're going to feel the force. But if we try the same scenario, and this time you're wearing a glove, okay, so the same hand, sorry, this is a funny looking hand, but this time you're wearing a glove, and the glove kind of provides a cushion, then what's going to happen is you've increased the time slightly. You still have the same change in momentum, whatever the speed is, right, for example, 3 meters per second, and the ball, let's say 0.5 kilograms, then the momentum is going to be 1.5, because the final momentum is 0, because the velocity will be 0. So it's 1.5, and in this case, it's also 1.5. So it's 1.5 here, 1.5 here. What's the difference? The difference is the time. The time is the difference. The time in the top scenario was less. It took 0.01 seconds for the ball to stop, which means the force was quite high. That's why you feel the force in your hand and you go, ouch, that was sudden. But if you wear a glove, okay, or if you take your hand back as you're catching the ball, what you've done is you've increased the time it takes for the ball to stop. And therefore, that change of momentum takes slightly more time. And since you've increased the time, you've decreased the force. The impulse stays the same. It's, change in time multiplied by force. But the forces and the times can be different. Okay, so here we have a few problems we can work through. All right. The first one says, a force acts on a bicycle for 12 seconds and changes its momentum. Okay? From 15 kilograms to 15 kilograms meters per second in the positive x direction, 15 kilograms dot meters per second to 38, something from 15 to 38 kilograms dot meters per second in the positive x direction. What are the magnitude and the direction of the forces? So we already know the formula, so change in momentum. Oops, let me just write that properly. Change in momentum is going to be corresponding to the force multiplied by the change in time. Okay, so in this case, the change in momentum is going to be 38 minus 15. So that's easy. 38 minus 15. Which is 23, because that is PF. And this is, and this is PI, which is the initial. (23 kg dot meters per second). Are we done? Are we done? No. What is it asking for? It's asking for the force. Now we need to find the force. Okay, and what is the force equal to? The force is equal to change in momentum, which is what we just found, divided by the time, which is given to us from the formula, from the question. So the force is equal to 23 divided by 12 seconds, divided by 12 seconds, which is equal to nearly to 1.9. Yep. 1.9 newtons. Okay, right. Let's go to question 17. Question 17 says, an impulse of 12.2 kilograms dot meters per second is delivered to an object whose initial momentum is 4.5. The impulse has the same direction as the initial momentum. What is the object's final momentum? Okay, well, remember what is impulse. Impulse is the change in momentum. So impulse is equal to P final minus P initial. P final minus P initial. And so that equals, what do we have? We have the P initial. We are trying to find P final. And we have impulse. Okay, so let's rearrange this. Sorry, it's going to be P final equals change in momentum plus P initial. Okay, that's just simple rearranging. If you move the minus pi on this side, move it to the other side, then that becomes P, a change in momentum, plus Pi. And so it's going to be 12.2 plus 4.5. 12.2 plus 4.5, that equals 16.7 kg dot meters per second. Okay, let's move on. Here we have example 7.5, rain versus hail. A person stands under an umbrella during a rain shower. A few minutes later, the raindrops turn to hail through the number of drops hitting the umbrella. Though the number of drops hitting the umbrella per unit of time and their speed remains the same, is the force required to hold the umbrella upright in the hail greater than, less than, or equal to the force required to hold it in the rain? Interesting question. So we've got a person holding an umbrella, and we've got drops of rain falling down, and then we've got hail falling down. And we're assuming that it's the same number of hail falling down as raindrops. And is the momentum going to be the same? No, the momentum is not going, sorry, the impulse, is it asking for the impulse or the momentum? Is the force required to hold the umbrella? Okay. No, it's going to be more for the hail. Why? There are two things at play here. The first one is when a raindrop hits an umbrella, it spreads, okay, it breaks apart. And you know, if you remember that example from the previous video with the beanbag teddy bear and the ball, when the ball bounces back up, it has momentum in the upward direction as well. Whereas rain is a bit like that beanbag, so when it falls, it doesn't have that back upward bounce, whereas the hail would. So that's the first thing that I'm thinking about, is that the hail, when it bounces off the umbrella, okay, it's going to have momentum in the upward direction as well. So the change in momentum, or the impulse, is going to be higher, and the force is going to be higher. The other thing is the mass of the hail is usually bigger as well. And we know that momentum is equal to mass times velocity. So assuming the mass is bigger, that means the momentum is bigger, and since impulse is about change in momentum, then the impulse is going to be bigger and the force is going to be bigger. So either way, the force is going to be bigger because the hail is bigger, and therefore the momentum is going to be bigger because momentum is related to the size of the hail. And the other thing as well is because there is a bounce, there's momentum on the upward direction as well. So either way, it's going to be, the force is going to be bigger or greater than. Right, moving on. I think I'm bored of this color. I'm going to change it to purple. Three friends push a stalled car. A stalled car just means a car that's stopped, and its driver to a nearby service station. Assume the car rolls without friction on a smooth and level road. If the car is at rest initially, and the three students give a combined push of 305 newtons, what is the momentum of the car and the driver after 12 seconds? If the mass If the mass of the car is 1,360, what is the car's velocity after 12 seconds? Okay, so the first thing we need to work out, assume the car is rolling without friction as well. If the car is initially is rest initially, so that means the initial momentum is zero because it's saying the car is at rest initially. And then the students give a combined push of 305 newtons. What is the momentum of the car after 12 seconds? Let's write some formulas. That's always very important. P is equal to force multiplied by change in time. We have the force, 305, and we have the time, change in time, which is 12 seconds. So we know that the change in momentum, so what is the momentum of the car? The momentum of the car is equal to, change in momentum is equal to PF. What am I doing? You can tell it's late. Just by the way, I'm making these silly mistakes. PF minus PI, and it is late. It's about 3 o'clock in the morning. Not that it matters. Let's have a look. PI is going to be 0. Why? Because it says it's at rest, which means it's the PI is going to be mass times velocity. Velocity is 0. So, and if velocity is 0, then that means the whole thing is 0. So there's no PI. Okay? PF is going to be, that's what we're trying to find out, right? I think that's what we're trying to find out. So the change in momentum is equal to PF minus, it's just PF. That's what it is. So what is the momentum of the car after 12 seconds? Well, it's just going to be, change in momentum is PF. So it's going to be 305 newtons multiplied by change in time, which is 12 seconds. So it's just going to be that, which is going to be equal to approximately 3,100 and something. 305 multiplied by 12 seconds, 3,660 kilograms dot meters per second. That's part A. Part B, if the mass of the car and the driver is 1,360 kg, what is the car's velocity after 12 seconds? So we already know that momentum is equal to mass times velocity. So we have the final momentum. Momentum is equal to mass times velocity. We have the final momentum, which is 3,660. We have the mass, which is 1,360 kilos, multiplied by velocity. So it's 3,660 divided by 1,360, something to the effect of 2.5 to 3. 3,660 divided by 1,360. So the velocity is going to be 2.7 meters per second. Okay, hopefully that's not too bad. Okay, let's move on. Question 18. Suppose one of the three students in the guided example in 7.6 stops pushing the car after 6 seconds. In this case, uh, the force exerted on the car is 305 for the first 6 seconds and 215 for the second 6 seconds. What is the final momentum of the car? So, once again, I'd like to draw the triangle. Change in momentum equals force multiplied by change in time. And we are doing question 18. And we are going to be doing A. Now, what is going to be the force? Now, we got to work out the final force after 12 seconds. But remember, for 6 seconds, it's 305 newtons. And then for the next 6 seconds, it's 215 newtons per second. So let's just do that first. The total force is going to be 305 multiplied by 6 plus 215 multiplied by 6. And that equals 305 multiplied by 6, 215 multiplied by 6, and that equals a total of 3120 newtons. 3120 newtons. B. What is the final speed of the car? What is the final speed of the car? Interesting. How do we work out the final speed of the car? Well, first we have to calculate the final momentum, right? Which we did. And then once we have the final momentum, we can divide it by the mass of the car. Do we know the mass of the car? Well, turns out in the previous example, we do know the mass of the car is 1,360. So, remember, P equals mass times velocity. So, let's do another triangle. P equals mass times velocity. So we have, what are we trying to work out? The final speed, which is velocity. And so velocity is equal to P divided by payload divided by mass, which is equal to 3,120 divided by 1,360, was it? Yep, 1,360. 2.3 meters per second. So it slowed down a bit, and that's because the student stopped pushing. Okay, I'm going to take this off because I need the space. Sorry. I hope you're giving these a go and you're working with me. So basically what I want you to do is I want you to pause the video and try it yourself, then check your answer with me as I go through it. Question 19 says a baseball player bunts, that means hits softly, a 0.144 kilogram baseball thrown at 43 meters per second. The bat exerts an average force of 6.5 times 10 to the power 5 or 10 to the power 3 newtons on the ball for 0.00122 seconds. What is the final speed of the ball? What is the final speed of the ball? Interesting question. What is the final speed of the ball? So, let's see what we have. We have the mass. We have the velocity initially. Oh, okay. Just a second. I'm going to try and draw this. So we have the ball. Here's the ball. Mass 0.144 kg. And traveling up 43 meters per second, right? And then it's being hit with a force of 6.5 times 10 to the power 3 newtons. But then here's something very important that I need you to pay attention to. I hate this kind of question because it's just kind of like a little bit tricky. Excuse me. So here's the issue. It's right there. Assume the ball is bunted directly back to the pitcher. So what that means is assume the ball is being hit straight back to the pitcher. So assume the ball is traveling in this direction now. With a force of so and so and so. So that means this force is actually in reality negative 6.5 times 10 to the power of 3. This is very important. If they hadn't said that, it was bunted back, then I would have left the force exactly the same. But because it was hit back, now it's a slightly different situation. And I'll tell you why that's important. Because otherwise the speed would be a lot higher because we are assuming that it's bunted forward, but it's not. It's bunted backwards. So that means it opposed the force. Okay, anyway, let's work out the initial momentum. The initial momentum is going to be, Pi is going to be 0. Mass times, of course, mass times velocity, which is 0.144 multiplied by 43 meters per second. 0.144 times 43, which equals 6.192 kg dot meters per second. Now, of course, when I'm working as I'm working, I'm not rounding. I'm not looking at significant figures just yet. I'll do that right at the end. The answer at the end, that's when I worry about rounding and significant figures. As I'm working at the moment, I'm not going to round anything because then I get an error. So that's the initial momentum. Okay. And then we have change of momentum is equals to force times time. And then we have the force, which in this case is going to be negative 6.5, negative 6.5. So now what I'm going to do, okay, I want you to listen very carefully to what I'm doing. I'm working out the change in momentum. I know what the initial momentum is, and now I'm working out the change in momentum using my negative force. So that's going to be F multiplied by change in time. So, and I'm going to use negative 6.5 times 10 to the power of 3 multiplied by the change in time, which is 0.00122 seconds. Negative 6.5. Why negative 6.5? Once again, I'm going to remind you because it is opposite to the initial velocity. It's opposite. It's directly opposite. So multiplied by 0.00122, and that gives me a change of momentum of negative 7.93. That is the change in momentum. Okay, that is the change in momentum. And of course, the change in momentum is equal to P final minus P initial. This question is proving to be a bit tricky, actually. We've worked out P initial. We're working out P final. Change in momentum is P final minus P initial, so it will be negative 7.93 equals P final minus 6.192. So P final will be negative 7.93 plus 6.192, which is equal to negative 1.738. Holy moly, we still haven't even worked out the speed. This is crazy. This is one crazy question, really. Once we work out now once we work out the P final, which is what we just worked out here, now we can work out the speed of the ball, because now we use this P final equals mass times velocity final. We're trying to work out the final velocity. So it's going to be that divided by the mass, 0.144. Oh my goodness. So anyway, so it's going to be that divided by 0.144. I'm running out of space. Divided by 0.144, which is equal to 12 meters per second, or negative 12 meters per second. And that makes sense. So it's 43 meters per second this way, and then negative 12 meters per second this way. Okay, that question was nasty. Don't worry, I will never be asking you anything like that. Or will I? No, I won't. Yeah, I think the worst part about this question is realizing that the force has to be in a different direction to the initial momentum. Okay, there are quite a few steps there. Okay, let's take all of this away and try and do question 20 now. So question 20, when spiking volleyball, that's when basically when you're jumping and you're hitting the ball initially. When spiking volleyball, a player changes the velocity of the ball from 4.2 meters per second to negative 24 meters per second. Okay. Sorry, that's not the surf. That's not the start. That's basically when during volleyball, when people are playing, this is the volleyball net, and so if somebody threw the ball this way at 4.2 meters per second, and then somebody hit it and then tried to get it down here at negative 24 meters per second. So they repelled the ball in the opposite direction at a much higher speed. If the impulse delivered to the ball by the player is negative 9.3 kilograms dot meters per second, what is the mass of the volleyball? Interesting question. It's so we have the change in momentum because that's right there, the impulse, which is the change in momentum. Change in momentum equals force times time, right? But we don't have force or time. What we have is change in velocity. Now, this is kind of another tricky question in a way, because what is change in momentum? That is equal to P final minus P initial. And what is the formula for P final? It's going to be mass times Vf minus mass times Vi. So this is what we are given here, right? This is what we are given. So basically, it's going to be, another way of putting it is change in momentum, sorry, is equal to mass multiplied by change in velocity, because the mass stays the same. And we are being asked to work out the mass. So since we know that, so we know that's basically it. That's another way of rearranging the formula. You don't need that. So it's going to be change of momentum equals mass times change in velocity. Which is equal to negative 9.3 over change in velocity is Vf minus Vi, which is minus 24 minus 4.2, which is minus 28.2, and that will equal the mass, which is about a third. 0.3 kilograms. Is it exactly a third? kg. Okay. So I hope that wasn't too hard. Let's have a look. Question 21. As an orange falls vertically down, its momentum changes by 2.4 kilograms dot meters per second. What is the weight of the orange? Okay, 21. Remember, change in momentum is equal to force times change in time. Force, that's weight. They're asking about weight. So just thinking about it. That's crazy. That's just the same. It's per second. So the time is 1 second, and the change in momentum is 2.4. So the force, or the weight, in this case, the weight force, is equal to change in momentum over 1 second per time, which is equal to 2.4 divided by 1, or 2.4 newtons. Yeah, so the mass will be 10 times less than that, so 0.24 kilograms, which makes sense. Like all tricky questions today. Right, and B, how much time does it take for the orange's momentum to change by 6.1? I'm going to use the same formula. So if I want to change the momentum to 6.1, and I have the force, I'm trying to work out the time, right? So change in time equals change in momentum over the force. So it's going to be 6.1 divided by the force, which is, I just worked it out, 2.4, 6.1 divided by 2.4, and that is 2.5 seconds. It's going to take 2.5 seconds. Next. Yay, lesson check. Let's have a look. Identify which one or more of the following quantities has the same direction as impulse. Which one or more of the following quantities has the same direction as impulse? And I have what to work with here. So we have momentum, change in momentum, velocity, force, kinetic energy. Remember, impulse is change in momentum. Impulse is change in momentum. So this is definitely one of them. That's the same direction. But also impulse is equal to the force multiplied by the time. Time is not a vector quantity. Time doesn't have a direction. But these two are the same. So it's also the force. So change in momentum and force. Question 23 says, explain, does impulse, sorry, let me start labeling these. Does impulse determine an object's momentum or the change in an object's momentum. Impulse, by definition, is the change in object's momentum. It's P final minus P initial. So obviously it is going to be the change in momentum. It's momentum. 24. Why would a thin steel helmet offer little protection during an accident? Okay, so that's like wearing a very thin glove. Okay, so what would be the difference in wearing a very thin glove? Like just imagine your hand here and then somebody throws a really hard ball or an orange. Okay, somebody throws an orange at you and you try and hold the orange or try and slow down the orange with your hand. If you're wearing a really thin glove, like a surgical glove, what's going to happen is it's going to hit and the time is going to be quite low. So here's the difference. Change in the momentum is equal to force multiplied by change in time. So it's all about this guy here, the time. If you're wearing a thin glove, then the orange is going to slow down in a very short amount of time. The impulse will be the same because impulse is change in momentum. Let's say the scenario is as such. The ball, here's the orange, and here's the orange. And the glove is over here. Now, if you have a very thin glove, I'm not going to draw a glove, I'm just going to draw the layer. If you have a very thin glove versus a very thick glove, a very thin glove means, look, the change in momentum is going to stay the same here and here because the initial speed is 3 meters per second and the initial speed here is 3 meters per second. The initial weight is 0.5 kg. The same scenario I'm explaining as before. So the initial momentum is 1.5 and the initial momentum here is 1.5. The final momentum is 0 and the final momentum is 0. How do I know it's 0? Well, the ball stops. The ball stops, or the orange stops. So PF is 0 and PI is 1.5. That means change in momentum is 1.5. In both cases, it's going to be 1.5. But what's different when I'm wearing the big glove compared to the small glove? Why does it feel less? Because the force is going to change. Why? Because the time is going to change. The time in the initial scenario, this scenario here, the time is going to be less and therefore the force is going to be higher because this is staying the same. It's not changing. So the momentum, the change in momentum will not change, but the force will change. When you are wearing a thin glove, the force is higher compared to when you are wearing a thick glove. The same exact scenario with a helmet. If it's a thin sheet of metal, it means your head is going to slow down very quickly and not take a long time, and therefore the force is going to be very high. What kind of protection is that? What kind of protection is that? If the time it takes your head to slow down is not long at all, that's like just hitting your head. That means you go from 100 to 0, and that means you're just going to, the force is going to be so high it's going to crack your skull. What you want to do is you want to wear a helmet that has a cushion, and if the helmet has a cushion, then it's going to slow down your time. So it's gonna extend your time, and therefore the force is going to be less. So why would a thin helmet means short time and much bigger force? 25. Rank the systems in order of increasing impulse. What do we have? Change in impulse equals force times change in time. What do we have? We have force and we have time. I'm going to treat every F like it's 1 like by the coefficient, and I'm going to treat every t by the coefficient. So the first one is 1 times 1, so that's 1. The next one is 2 times a third, so that's 2/3. The third one is 5 times 1/10, which is 5/10 or half. And the fourth one is 10/100 or 1/10. Now, since it's asking for increasing, so it's going to be DCBA. DCBA. D is the smallest, and A is the biggest. 26. An unattended car rolls slowly across an empty parking lot. Consider the following two cases. In case 1, the car hits a light pole and comes to rest. In case 2, the car hits a pile of plastic garbage bags and comes to rest. Either way, it was traveling at the same speed and then it came to rest. That means the change in momentum is the same for both cars. Okay? It's traveling at the same speed, it comes to rest. So the impulse is the same, the change in momentum is the same, the final momentum is the same, the initial momentum is the same. So the change in momentum or the impulse is the same. So it's saying, is the impulse in case 1 greater than, less than, or equal to than the impulse? It's equal. The second question says, is the average force in case 1 greater than, less than, or equal to? Now it's different. Because in the first case, it hit the light pole, so that means it stopped suddenly. It stopped in a very short amount of time. So therefore, the force is going to be a lot higher. In the second case, it hit the garbage bags, and therefore the slowing down happened slowly. As in the change in speed, the change in momentum happened over a longer amount of time. So therefore, the force is less. When you increase the time, you reduce the force. Increase the time, reduce the force. That's why helmets work. That's why crumble zones work on cars. That's why we have seat belts that are slightly stretchy. All of these things that seem a little bit trivial, they actually make a huge difference, because what they are doing is slowing the impact even by fractions of a second, but it makes a huge difference. Question 26, we answered it. So it's going to be, is the average force in case 1 greater than? It's going to be greater than in case 1 because that's the case that hits the pole. A safety helmet extends the time of impact from 0.005 to 0.02, so by a factor of 4. Oh, okay, that was the question. By what factor is the average force 4? So the force has been reduced 4 times, so it's going to be 25% of the force. Can you imagine that? So a helmet with a bit of cushion, even though like the time is really short, but since the time has been extended slightly, like 4 times, the forces now has been cut by a factor of 4. It's crazy. So instead of experiencing 100 newtons worth of force on your head, you're now experiencing 25 newtons worth of force. Physics works. Okay, question 28 says, in typical golf swing, the club is in contact with the ball for about 1/1000th of a second. If the 45-gram ball acquires a speed of 67 meters per second, estimate the magnitude of the force exerted by the club on the ball. Okay. So question 28 is asking for the magnitude of the force. So the magnitude of the force is going to equal the change in momentum over time. Where do I write this? Question 28, I'm going to do it over here. It's going to be the force is going to be the change in momentum over the time. Yes? Yes. What is going to be the change in momentum? How long is the ball in contact with the with the club, 0.01 seconds. So it's going to be the momentum is going to be mass times velocity, and the initial velocity is 0, so the change in momentum is just going to be the final mass times velocity. So it's going to be 0.045 multiplied by final velocity minus initial velocity. But we don't have an initial velocity. An initial velocity is 0, so only the final velocity, which is 67. That is the change in momentum. And the time is 0.001 seconds. Whoever was writing these questions about momentum was having, about impulse, was having a bit of fun, I think. The force is going to be 3,015 newtons. Since we are working with two significant figures, I think it would be sufficient to just say 3.0 times 10 to the power of 2 newtons. Okay. And the last question says, calculate a 0.5 kilograms croquet ball is initially at rest on grass. Okay, I'm gonna stop there because that's an hour. I want you to try and work out the last one on your own, okay? The croquet ball problem, I want you to work that on your own. Okay, thank you very much. Like, share, and see you على خير. Assalamu alaikum.